I'm Professor Shivanand Kanavi, convener of the NIAS Literary Arts and Heritage Forum here at NIAS. And I'm delighted to welcome you to what promises to be a very exciting lecture on the Quantum Centenary, 1926 to 2026, Achievements and Unresolved Issues by Professor Shivanand Kanavi, eminent business, economic and science historian and journalist, also adjunct faculty here at NIAS. And Professor Kanavi is a theoretical physicist by training at IIT Kanpur, IIT Bombay and Northeastern University in Boston, USA. And after a brief academic career, he became an economic consultant and a business journalist, ending his professional career as Vice President in TCS of the TATA Group. And he continues to write in the media and lectures widely on science, technology, Indian business and economy. And really he's a Renaissance personality with multifaceted interests. And the last talk he gave here was on the historical perspectives on the historical and philosophical basis of the Lingayata movement and so on. So it's wonderful to welcome him back here. And today, of course, he's going to be talking about a very interesting topic, as this past year has marked a historic occasion, the centenary of the birth of quantum mechanics. In July 1925, Werner Heisenberg submitted a paper to Zeitschrift für Physik entitled On Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relationships, thus giving rise to quantum mechanics. Thereafter, the field of quantum mechanics emerged through the pioneering efforts of physicists such as Werner Heisenberg, Erwin Schrödinger, Max Born, Dirac, Pauli, and others. And their groundbreaking contributions unraveled the mysteries of the atomic world and transformed our understanding of reality itself. Quantum mechanics stands as one of humanity's most profound intellectual achievements. Its foundational principles, quantization, wave-particle duality, probability, uncertainty, and superposition dramatically reshaped our conception of the universe. And as an eminent historian of science, Jagdish Mehra, observed, the birth of quantum mechanics presents us with one of the most remarkable episodes in the history of science. So this is an extraordinary scientific and human story behind the development of a theory that revolutionized modern physics and continues to underpin much of contemporary science and technology, and has also inspired a lot of art and theatre and so on. And over the past century, quantum mechanics has paved the way for advances in quantum field theory, computing, and modern technologies, which are also relevant in terms of conceptual aspects, such as in the field of AI, and so on. And Heisenberg noteworthily said, the history of physics is not only a sequence of experimental discoveries and observations followed by the mathematical description, it is also a history of concepts. Well, I couldn't resist going off into this long preamble as I did a BTech in IIT in engineering physics in the late 80s. And I remember in those days the excitement of learning about wave-particle duality and the thought experiments of Schrödinger's cat dead or alive, the square potential well, and so on, all these mind-boggling aspects. And though I've moved away a lot, I look forward to being taken back to my EP classroom today, and of course having the further developments being unpacked with our erudite and articulate speaker, Professor Kanavi. And of course, although our forum mainly looks at heritage, we also are very interested in looking at scientific heritage, so this is very exciting for us to have this lecture here. And over to you, Professor Kanavi, and very warm welcome to you.
Hello. Thank you, Dr. Sharda. She's a good friend of mine, so she added a bit of more to what was wrong in my bio. I feel very happy to come back to NIAS after some time and have an interaction with the people here. I chose this topic because there have been, of course, a lot of seminars and webinars and erudite conferences on this in the past year in many institutions of higher learning. But this is not aimed at that kind of audience or that kind of a content that I'm presenting. you can say, almost say this is a journalistic view of quantum centenary, quantum century. So if you are practicing physicist, then you might find it superfluous what I'm saying, or many things, just a repetition of what you already know. And if you are not physicist, then hopefully you will get some look-see into this very complex, mathematically complex, conceptually confusing, but a subject which has yielded so much in practical technology, which has changed our life at least in the last 75 years. So that makes it, I think, if not for the abstract mathematics and the complex philosophical questions it raises, that makes it interesting even for lay people to get to know something about this new exciting physics that came up in the beginning of the 20th century and then actually took off into the modern quantum mechanics about 100 years ago. So there may be a little bit of dispute on should it be 25 or 26 because Schrodinger's paper appeared in 26 and one of the early papers of Heisenberg appeared in 25 and Dirac's PhD thesis appeared in 26, which sort of synthesized both and gave it a totally new way of looking at quantum mechanics. But leave that aside, that's just a technical issue for historians to argue. Now, to motivate lay persons to get into the intricacies of this subject so that they'll start reading at least popular science books on quantum mechanics, I just want to take you back to what existed before quantum mechanics. Because when we say a revolution, some revolution has happened, people living the revolution will never realize it. Okay? I've seen it a lot of times talking to younger people, for example, talking about digital revolution. When I say that, I had to go to the post office and book a call to make a call anywhere in India or abroad and wait 2-3 hours, their faces are totally blank. Because today they can sit with a mobile phone and not only talk to anybody, do a video call, right? Using whatever n number of apps. And so why go to a post office and so on and so forth, right? So for them, whereas we all lived through that in the last 50-60 years, we lived through an era when there was no digital technology and then there was digital technology and today it is just in every aspect of our life. So we can see the revolution which younger generation doesn't. Maybe they are looking at something else, which they are looking at probably possibilities or problems with AI and things like that. Whereas for us, AI is still question mark, what it is and what it can do, what it will not do, etc. Maybe some people are saying it's a bubble, some people are saying it has raised too many expectations, some people are raising moral and ethical questions, sociological questions and all that about it. Whereas some people are absolutely thrilled about it, at least Silicon Valley venture capitalists, and they're going really utopian or dystopian view of the world. I just want to go back to the pre-quantum thing. That is let us say, what was life like before the quantum revolution? So I am just calling it 20th century, but basically you can say latter half of the 19th century, 1850s, 60s onwards, what affected our life. And in that, we saw telegraph, we saw the telephone, we saw 19th century, radio came, right, with Marconi later, even electronics came, right, valves. I don't think very many of you have seen a valve radio. We all used to listen to, Akashvani and AIR, etc. on a valve radio, big clunky ones. So electronics started with the valves. Even computers started with the valves, the early computers. Television started without any modern electronics, no transistors, etc. That is in the 1920s. Cars, buses, highways, all these came into being. None of them existed in the earlier period. It's only with the developments in the internal combustion engine and by diesel and Benz and and all that and the thermodynamics of Carnot cycle and all that going together, that you saw the automobile coming in, right? Electric lighting came in, and there was such a revolution. All these were revolutionary, right? If you look at the medieval living of human beings, and even in Europe, where most of these things, these inventions were done, even 17th century Europe was nowhere like what it was in the 19th century, right? All these things came in. Electric lighting came in, it changed our lifestyle. People used to either go to sleep after the sun went down, or use a kerosene lamp or a candle or something to do whatever little thing they could do in the night. But electric lighting changed all that with Edison's bulb and all that. And then of course you had to have a generation of power and supply of power and transmission, generation of electricity, etc. Right? Weapons of war, all these modern weapons, guns, modern guns, bombs, tanks, ships, submarines, missiles, radar, all this came up in the 20th century. Right? Airplanes, which had not only the principles of aerodynamics developed and all that, and right brothers flew the plane, and then the jet engine was developed, all this happened. And by the way, none of this actually need quantum mechanics. All these are products of what you can say classical physics, chemistry, biology, engineering, and all that. So you can say almost our modern way of life, what we call modern way of life in the 20th century, is shaped by classical sciences, classical engineering. It didn't need quantum mechanics. Now of course we use many of these same gadgets with quantum mechanics technology which has been produced by quantum mechanics embedded into it, so qualitatively they are much more advanced. But the basics of all these things did not need quantum mechanics. None of these gadgets needed quantum mechanics. Satellites actually didn't need quantum mechanics. That means there was no quantum technology in Sputnik or even Saturn V. Okay? Yeah, rocketry came up much before quantum mechanics came in. Right? Werner von Braun developed it in Germany, NASA developed it, the Russians developed it, they put the Sputnik, they put even a man, Gagarin and Tereshkova in the orbit. So none of that had anything to do with quantum mechanics. Even the calculations were done by hand. You might have seen there is a famous Hollywood movie now going on, which shows women who are computing the orbit of the, I think it was even early Apollo mission, I think, if I remember right. And they were not using computers for that. And they were called computers. People were computing, were called computers, not machines. Okay? And anyway, but they never got the credit for it, so they are being remembered now. That history of NASA itself is being remembered now. Landing on the moon, even Apollo there was hardly any quantum devices in it. Maybe elementary, some chips were coming in. I don't know how many chips were used. Microelectronics was used in the Apollo mission. I'm not sure about that. Then of course, planetary exploration, unmanned to Jupiter, to all the Voyager and all that Venus missions, all sorts of things started. None of this, and all the telescopes, from optical to radio telescopes and all that, they didn't need quantum mechanics. You can make them more powerful with quantum technologies. That's a different thing. And of course, electric motor, dynamo generator, even before that, right? Faraday's work and so on started that, and that's how the electric power came, was generated and later used in the Industrial Revolution, latter part of the Industrial Revolution, when they switched from steam to electric power. Trams, trains, right? When we talk about Dadar TT in Mumbai, people don't know what TT stands for. TT is tram terminus. right? Because trams were running around all over Mumbai, all over Calcutta, and of course maybe now it's a curiosity in San Francisco, right? They call it streetcar, I think, but it's a tram. And trains, the normal steam trains, and then diesel, then electric, all these. So all these are typically, I'm just saying, 20th century life. Okay? Modern medicine. From Bayer's aspirin onwards, when he boiled some willow tree bark and then produced this salicylic acid compound, and which he treated his father who had arthritis and so on. That's how the aspirin came. And then the whole modern synthetic medicines and all these things started. Otherwise, there's a lot of course, herbal medicine, natural product chemistry, things, and traditional medicine systems existed. But modern medicine, what we call today modern medicine, all of this came from traditional chemistry. Plastics, all the plastics, paints, man-made fibers, nylon, rayon, terylene, acrylic, all these things which changed our clothing, fertilizers, pesticides, tractors, hybrid seeds, right, which revolutionized agriculture, right? Films, photography, and so on and so forth. So all these are products of classical physics, chemistry, biology, engineering, and industrial revolution of 18th to 20th century. And even you can say to almost first half of the 20th century, not all of 20th century. I'm dividing it. The dividing line is 1948. Because that is when Bell Labs invented the transistor. So, semiconductor research led to the development of transistor. And when the transistor came, and when the Bell Labs people gave a press conference, I think they gave it in New York City, and the journalists asked them, okay, this is nice, it's amplifying something, signal, what is it good for? So the Bell Labs person could not see what the transistor is going to be used for. So he said, I think it will lead to a better hearing aid for people who are hard of hearing. Okay? And today we know, everywhere you see transistors in a chip, which are in billions in one chip, right? Everywhere, and these chips are everywhere. And the transistor, think about transistors, and the even concept of a semiconductor is totally a quantum effect. Otherwise, you have conductors and insulators. What is a semiconductor? What is something called a barrier? What is energy bands? What is conduction electrons? And all these things. What are you doing by changing the potential across a barrier? When two different N-type and P-type semiconductors are joined. All these things. These are all quantum effects, right? Classical physics doesn't explain why tunneling should happen, right? That's all. So that is when we can say quantum technology started actually, quantum physics started leading to technology which started changing our life. The physics itself started from beginning of 20th century and took a very distinct shape in 25-26, which Schrodinger, Heisenberg, Dirac, and so on. But its effects started coming 25 years later with the semiconductors. Right? So all these things that we see, transistors and semiconductors, microelectronics and chips, all these are latter part of the 20th century. And now of course they are everywhere, they are ubiquitous. Today I was quite surprised 2 years back when there was a shortage of chips for Indian automobile industry. I am not talking about very advanced automobile industry. I am not talking about Toyota, Mercedes, BMW or BYD or something. I am talking about Indian automobile industry. When they faced shortage of chips, because a lot of it, there was a problems with the supply chains and a lot of it used to come from China and so on. That I came to know that an average Indian car has about 1500 chips today. 1000 to 1500 chips in an average Indian car, right? So it's not that is the extent, we know every gadget we use, microwaves and washing machines and television sets and of course mobile phones, everything is full of chips, all depending on transistors and so on, right? So all these are the later part of the digital revolution, products which we are using, right? This is the plumbing and the groundwork which you may not see outside, but the products, consumer products are there in mobile phones and all these other things, laptops, even the nowadays you wear a wearable, right? A small watch-like thing which counts how many steps you walk. How does it know how many steps you walk? There is MEMS. There is a nanotechnology, okay, in it. Accelerometers in it, which can see the slight shocks that happen when you take a step and it counts. So that's how it measures how many steps you walked, right? And it doesn't do it because sitting in a car and wearing it. I tried it. Okay, very bad ones also start clicking when you're sitting in a car, but good ones don't. Anyway, so, and of course, our entire way of communication changed. When Satyendra Bose thought up these new statistics for photons, he sent a letter to Einstein, and he didn't know Einstein, but far away sitting in Calcutta, they were translating Einstein's lectures. In fact, his 3 lectures on principles of relativity, the first English edition came from Calcutta, I think in 1917. They translated from original German into English and published it. And probably with Bose was Saha also in that particular endeavor. M.N. Saha, well-known astrophysicist later. So he considered Einstein as his guru, though he had never met him. So he wrote a letter to Einstein saying, "Sir, etc., that if you think this is worth publishing, then can you forward it to a publisher?" Right? And that letter obviously took 3 months to reach Einstein. He had to go and ship, right? And Einstein looked at it, at least it was good luck of Satyendra Bose that Einstein just didn't discard it. Some letter come from India, Calcutta, something he's talking about physics. And then, so he looked at it, he found it very interesting, added some things to it, and then he forwarded it. And it was published. And that's how the whole new way of counting of the statistics of photons that came into being. That revolutionized so many things later. In fact, 4 or 5 Nobel Prizes I can count which are based on this work, based on these statistics at a foundational level. Okay? Though of course, Bose never got a Nobel for his contribution. But the reason I'm saying this is, today you don't have to wait 3 months, right? In a millisecond your email will go to the publisher, to whoever you want to collaborate with, whoever you want to refer to, and so on, right? So whole way of communication changed, transactions changed, right? All our financial transactions, commodity transactions, stock market transactions, banking, everything changed, right? And we can see it in India, in the rural India. I live in a rural part of Maharashtra, right? And literally surrounded by tribal Adivasi villages. And they use WhatsApp, they use digital payment systems. If I need some commodity from a nearby village thing, I just WhatsApp a list of things, groceries or bread, eggs, whatever I need, or meat. And that guy delivers it. And then I pay him on a digital payment. There are people there because it's a slightly touristy place. People come there to enjoy nature. It's a beautiful place and all that. So I asked some tribal kids, they were setting up some tent houses and some other things. I said, "What are you doing it for?" They said, "Oh, tourists are coming in the rainy season and we are doing it." I said, "But how do you get the tourists?" They said, "Oh, online booking was there." For the people who come and want to stay in those tents, most probably, fairly well-off people from Mumbai who want to escape the madness of Mumbai for a weekend and run there, to enjoy nature. But, so, this is absolutely widespread. This is not an elite or technology for the elite anymore. It is just become ubiquitous. Okay, many of its products and services. Similarly, of course, information gathering. I mean, I know how things have changed, at least in journalism. How things were in the pre-internet era and after the post-internet, and now, of course, you have even AI tools to do a lot of some basic work for you, some basic trends and so on. Of course, you have to do fact-checking and a lot more. You just use it as a base. Right? The AI doesn't tell you what is happening in a place. You have to go there, do the legwork and report, and maybe interview 10 different people reflecting 10 different points of view. But AI will tell you something else about about the history of a place or something like that. Whatever has been digitally recorded. Again, right? If it's in a book, AI doesn't know anything about it. So unless the book is digitized, right? So, and of course, media. We all know about how media has changed. Entertainment has changed, right? I mean, it started with Star Wars, that all computer graphics and all that in Hollywood, right? Star Wars and Pixar, that Industrial Light and Magic and Pixar and so on. Governance, how governance is being done, how are you making utility payments, how are you making tax filling and tax refunds, all sorts of things. Wherever government is interface. How it has changed. CDs, DVDs, lasers. Lasers is a purely quantum product. Okay. Spontaneous emission and induced emission was a path-breaking paper written by Einstein in 1905. Right. Much later, almost 50 years later, lasers and lasers were invented, which used that basic principles developed and led to coherent light and so on. Now lasers are used everywhere, including your remote, TV remote or any other remote. It uses a diode laser, and of course CD DVDs use lasers, and lasers are used for welding. I mean, and I'm not talking about some high tech. I went to Tata Motors factory in Dharwad, a small town in Karnataka. And there were these robots doing laser welding of the body of the automobile. Okay. Why? Because of precision. Now, this is not to save labor. This is because of the precision welding that only a laser welding machine and a robot could do, which was needed. Right? And of course, nuclear power, using nuclear fission for power and nuclear weapons, they are also product of the, you can say, quantum principles. Mobile phones, touch screens, digital cameras, solar power. Solar power, what is it? Right? You shine light on some material and it comes out with electrons. Now, how does that happen? Why should it happen? When can it happen? This is again a paper which was written by Einstein in 1905. And Einstein got his Nobel Prize for that, not for relativity. Right? So Einstein has to be, because he put forward the concept of the photon, quantized quantum, packets of energy, and what is the threshold frequency which is required for this to happen, electron to be emitted and all that. So that was a big jump in the old quantum theory itself in 1905. LED, now the lighting has changed now, right? Especially with the blue LED which was developed by Japanese scientists. Today we have white light coming from LEDs. Earlier there were only red and orange, gallium arsenide and these other LEDs. Now with gallium nitride compound semiconductors, we have white light. Now white lighting, that is saved, everywhere you see this LED lighting. So that is changed lighting, the economics of lighting also, right? Because technology has to do with economics, otherwise it remains esoteric. Great technology, but if it doesn't make things better, cheaper, faster, then it's of no use. It will remain in the back shelf somewhere, and maybe at a later date somebody will dust it out and at appropriate time to use it. Because a lot of communication technology was developed way before the chip revolution. But its implementation could only be done after the chip revolution happened. So a lot of the work was done in the labs in the 60s and 70s, which got that application in the 90s and around 2000. HD TV, MPEG and JPEG and all these things, MP3, all this new ways of data compression, data transmission, all these things became possible with the chip development. Otherwise, a lot of the theoretical work was done in 60s and 70s. Even cellular telephony was done in the labs. Okay. Of course, modern financial services, banking, and so on. Money, the concept of money. There's something called digital money. All your bank accounts are just some numbers, right? You don't see the cash, and you always worry what happens if something, somebody hacks into that thing, right? Or suddenly your bank account becomes zero, right? Then all your wealth is gone. Why? It's not something concrete. So neither is it cows and cowries, nor is it even paper money. It is just digital money, right? Entire medical thing. Sonography, CT scans, MRI, endoscopy, defibrillation, the pads you apply to revive a person who has had a heart attack, whose heart has stopped. Telemedicine, because defibrillation and even bullet trains, they use power transistors. Okay? What are called insulated gate IGBT bipolar transistors. Okay? Which are some things which were developed in the 70s and later, now they're revolutionized. Whole way of dealing with high currents and high voltages. Whereas there is a whole different science which goes into milliamperes and microamperes. Then how do you do with 1000 amperes and million amperes? How do you deal with that? You need a power control systems with power transistors. So, by the way, in many of these developments, Indians have played a role, but that's a separate issue. I'm not going to talk about it now. Laser surgery, okay, laser welding, modern cars I mentioned already, chips, sensors everywhere, all these gadgets which are all using fuzzy logic and all types of chips in it, sensors, right, washing machines, microwaves. Submarine internet cables, all our data in terabytes and petabytes is going through these submarine cables. All that uses, these not only fiber optics, but these what are called erbium doped fiber amplifiers, which you need to amplify because the signal weakens after a few hundred kilometers, even for the best of the fiber. So then you need to amplify and then resend it, right? So without that, you wouldn't have had submarine cables and giving you reliable and high-speed data with high bandwidth. In fact, that was a problem even in the old systems when you had nationwide networks of old telecom systems with copper cables. That you could not have, for example, in the US, a coast-to-coast call without having every few miles a repeater. So when AT&T worked on that, till the new technology came, it was not possible. But thousands of kilometers undersea, where nobody is there, to even repair it and all that. How do you send reliably petabytes of data when your financial systems, your security systems, and your almost everyday life depends on this data which is going around. So without these developments in semiconductor lasers, in fiber optics, in fiber amplifiers and all that, this wouldn't have been possible. Which is again plumbing, right? We look at the building and we don't worry about the plumbing, which makes that building survive and make it livable. And of course, the internet and AI and robotics and so on. So, without belaboring this point more, I just want to say, today our life is again very different from what it was in the 20th century. And all this is due to the digital revolution, and that digital revolution has been made possible by the application of quantum mechanics. Technologies which have come out of quantum mechanics. Okay? Semiconductors, lasers, etc., etc. So, these are all results of quantum revolution. Okay, now I'll just flash a few faces at you, and I think there are about 30 odd faces. You can say it's a subjective selection. There are many more scientists who were actually participated and various bits and pieces in this whole quantum revolution and made this thing possible. So I'm just going to run through them fast because there's not enough time. So even if I spend 1 minute for 30 slides, it will be 1 more hour. Okay, so please bear with me and just we'll run through them. Max Planck, first 1900, in fact, almost beginning of the 20th century, he said, talked about discrete character of energy and introduced the word quantum. It is said that later he got so fed up with what was happening in quantum mechanics, he said, why did I ever talk about this? In his autobiographical note somewhere this appears that why did I even talk about this sometime? Okay, because the edge that he introduced and talked about to introduce discreteness in energy, till that time energy was considered continuous. Okay, so discreteness of energy was for his own purposes, calculation. I am not going to get into that black body radiation issue, but he introduced the concept of discreteness of energy, so he called them quantum packets of energy. Okay. Thomson, he discovered the electron, very important thing. Einstein, I already mentioned you, he explained the photoelectric effect. Again, he had to talk about quantum of energy in the light. So we went back to the particulate nature of light, right? There has been a whole debate in the history of physics on what is light, right? So Newton said it's corpuscular, it's made up of particles. And he was able to explain whatever, reflection, refraction, whatever optical phenomena that existed at that time based on his theory. But then came others, Huygens and all that, who proposed that, light is wave. And then there were young experimenters like Young and all that, who showed through interference and diffraction of light that interference pattern and diffraction patterns of light can only be explained assuming light is a wave. Okay, only wave theory could explain it, not particular corpuscular theory. So there was this whole thing, and it was almost settled that light is a wave. Okay, but then comes Einstein in 1905, okay, of almost settled issue for 200 years. He says this can only be explained by assuming electromagnetic radiation is made up of light quanta of energy, and he called them photons. Okay, so it's quite a revolutionary thing. You can say going back to Newton, but qualitatively different. Then Rutherford, earlier the whole idea, these are just precursors because these are all important things in the quantum history itself. That first time he said that the battery is not made up of these neutral balls which were considered as atoms and whatever. And then he said no, these are not just some solid balls. The most of the mass in an atom is actually in a very small space in the center called nucleus, and the rest of it is almost vacuum. Okay, where the negative charge is floating around. So positive and negative together, the atom is neutral, but all the positive charge and most of the mass is concentrated in the center. And he experimentally showed that. Experimentally he showed that matter is made up of these atoms, and in these atoms most of the mass and positive charge is concentrated in a very small center. So you can say that is the birth of nuclear physics, the study of the nucleus. Okay? And then came, if that is the case, if here is a negative charge, here is a positive charge, in an atom which is neutral, how is that thing stable? Because the positive and negative charge should fall into the positive charge and become neutral. Why is it still hanging around there? And you already Thomson had formed these electrons as particles with mass, charge. They were hitting the small propellers and moving them. He used later, they found out what is called E by M ratio, the charge to mass ratio using electric fields, magnetic fields and so on. So particulate nature of electrons was already, you can say, established. So if these electrons are particles, and here is the nucleus with all the positive charge, then what happens to, why are these electrons not falling in? So then, they have to say no, they are not falling in. And if they fall in, they lose all the energy also, according to classical theory. No, they are going in these orbits, they are stable orbits and they don't lose energy by going in those orbits. Okay, so it looks like, Same thing happens in the solar system, right? There is a gravitational attraction. All the planets don't go and jump into the sun, right? You can say whatever they had some initial velocity, these planets when they're formed, so that they're trapped in the gravity of sun and they're going around. Okay? So they're not falling into the sun. Fine. So, and electric force is similar to gravitational force. Only thing is there is no negative mass and positive mass, but there is attraction. So if you look at attraction of the electron and the nucleus, then maybe electrons are going around like a planetary orbit. And that is what is the model which Bohr proposed. That an atom can be looked at as a planetary model. Electrons going around the nucleus. And then he postulated, you can say quite arbitrarily, without giving any reason, that these orbits are stable. There is no leakage of energy and all that. And only when an electron jumps from one orbit to another stable orbit, there is either an absorption, if it is going up, or an emission of energy. So there is a fixed amount of energy absorbed and emitted, not a continuous spectrum. Okay, so that energy, fixed energy, corresponds to a line in a spectrum. And experimentalists are already seeing lines in the spectrum of these various atoms. You have to explain that. Why, when you burn, see, with naked eye when you see something, some materials burning, like if you take a crystal of sodium chloride, your common salt, and burn it, then it gives a yellow flame, right? And some other things give you green flames and blue flames and all sorts of things like that. So you can say something to do with the constitution of that material is being reflected in the light that is emitted. But that light to naked eye appears like some continuous color. But when they looked at it with prisms and in the spectrometers, they found discrete lines here and not a continuous spectrum. So why discrete frequencies are being emitted or absorbed? This was a mystery which everybody had to explain now. Classical physics could not explain it. So Bohr came up with this thing and he said, this is what I am proposing, this is the way these orbits are, and whenever electron jumps from one to the other, there is an absorption or emission of the electron, and then he could do a calculation and say, more or less reflect the observed hydrogen atom spectrum and so on. Okay? And so that was considered a big advance. Then he also proposed something called complementarity principle. I am not going to talk about it here, but elsewhere we will talk about it. So then came Louis de Broglie, and there are very few PhD theses which changed the world. This was one of them. In his PhD thesis, he postulated that matter can also behave like waves. Now, for that time, it looked like a crazy idea. Okay? But by that time, already this duality, that light, sometimes, it is still diffracting and interfering in some, experiments. But in photoelectric effect, it acts like a particle, right? So duality of light was already being observed. And he says, why not duality in matter also? So why electron cannot behave like a wave? And if it does behave like a wave, what kind of wavelength can you associate with the mass of the electron? And so on, he proposed a hypothesis. He hypothesized one formula called a matter wave cycle. So he himself did not again realize its significance to future physics, and later he also relented. Why did I talk about this? Because he questioned quantum mechanics. De Broglie questioned quantum mechanics, just like Einstein questioned quantum mechanics later. Schrödinger questioned quantum mechanics later. Many of the founders of quantum mechanics, or who we call founders today, question some of the interpretations of quantum mechanics and its philosophy associated with it. We'll come to it later. But this was a revolutionary PhD thesis that of de Broglie. And Schrödinger, in 26, he proposed this famous wave equation, Schrödinger wave equation, and which correctly also led to calculation of the, again, hydrogen spectrum. And again, he could derive the hydrogen energy levels according to these, what is called a partial differential equation, as eigenvalues of that come out of this, as a solution to this equation, etc. And just around that time, or a little before, more or less you can say contemporary. Heisenberg had proposed another way of again explaining hydrogen atom spectrum, the light coming out of hydrogen, and he had used some constructs which looked like matrices, okay, because he had attended some math lectures in Göttingen. Göttingen had a very strong mathematics department, and so he was somewhat more familiar with vector spaces and linear algebra than normal physicists of that time. And so somehow he connected this to matrices, okay, and he came out with another explanation. So that was also called matrix mechanics by some people. Later he also proposed something called imprecision principle. This has also been called uncertainty principle, but the actual word he used in German means imprecision principle. It is not uncertainty, but it says imprecision. I'll talk about it later. Okay? But why we call that as a foundational paper is because again, his way of looking at hydrogen atom reproduces you can say, the hydrogen spectrum. So Schrödinger had one approach of differential equations and so on, and a wave function which is a solution for that, and Heisenberg had another approach. And then came Dirac, who almost at the same time, he did a PhD thesis, again another important PhD thesis, where he synthesized both. And he developed what is now known as a bracket formulation, where he looked at them as vector spaces, or what is today called a Hilbert space, and operators on the Hilbert space and so on. So that could unify both the Schrödinger's approach and Heisenberg's approach. So initial contribution of Dirac was bringing out how these two are equivalent. His 1926 PhD thesis. But of course what he is famous for is he developed the relativistically consistent theory for electron, because Schrödinger's way of looking at systems was non-relativistic. We write an equation which will look the same, what is physics called invariant, even if you are looking at it from another frame of reference, and so on. Okay, how can we make the equation invariant, or which in relativity is called Lorentz transformations? It should be consistent with that. Okay, so he wrote what was called Dirac equation, which was relativistically consistent. Fine, good, interesting development for formalism, right? It's just mathematics, right? But no, that development also posited that there should be an anti-electron. An electron with the same mass but with positive energy. Whereas electron has a negative charge, this should have positive charge, which was later called positron. And in that, this he proposed in 27, 28, and in 32 actually a positron was discovered. So he predicted, you can say, a positively charged electron. So that is one of the great, you can say, triumphs of theory, because otherwise mostly theory follows experiment, the experimental work. You have to explain the experimental data, and here he predicted something which had not yet been found. Okay, so that was a very great achievement of quantum mechanical theory and Dirac's theory. That which later came to be known as, okay, if electron has a positron, then why not all other matter also? So matter, there should be antimatter, and so on and so forth. And a lot of science fiction has been written on worlds made up of antimatter and so on, right? Anti-worlds, you can say. So then there was Pauli, his exclusion principle. I'm not going to, we think I'll totally run out of time now. So I'll just skip through this, just the names and what they're famous for. Pauli's exclusion principle meant that more than two electrons cannot be in the same state, and even those two electrons can be in a single state provided their spins are in opposite direction. That's it. Okay? Don't ask me now what is spin. I'll go to later. I'm just running through it. This is three people. Actually, I was looking for only Stern and Gerlach, because Stern and Gerlach, their experiment showed that not only energy is discrete, even what is called angular momentum, even that needs quantization. Okay, their experiment showed it. But when I was looking for the photograph, I found this rare photograph, and in between is this lady called Lisa Meitner. And I put this instead of those two people's portraits Because Lisa Meitner is one of those women physicists who did foundational work but didn't get the credit for it. She didn't get the Nobel Prize for actually explaining nuclear fission. Okay? Whereas she developed the theory of nuclear fission. Whereas Hahn and Frisch got the Nobel Prize for that. Okay? So there are at least half a dozen such women scientists who did the foundational work, but somebody else got the Nobel Prize and they didn't. And Lisa Meitner was one of them. I happened to come across this photograph, so I put this in rather than the individual photographs of Stern and Gerlach. Stern and Gerlach, of course, did a very important experimental work, which led to the quantum theory of angular momentum. Enrico Fermi, of course, all these people have many contributions. I am just telling you, in the history of quantum mechanics, what milestone did they achieve? Like Fermi did so many other things also. Each one of them has done so many other things. But he's famous for, he developed the first nuclear reactor where there was a sustainable chain reaction, controlled chain reaction in Chicago University, which was at that time called the atomic pile. Okay, that was the first this thing, which became the precursor to the modern day nuclear reactors, which produce electricity out of nuclear fission. And of course, he developed the theory of statistics of these electrons and all that, and so they came to be known as fermions. And there's a little anecdote about it I'll tell some other time, because it's also called Fermi-Dirac statistics. Apparently Dirac had independently written a paper on how electron statistics should be described. Then Fermi sent him a very polite note saying, "My dear sir, Professor Dirac had few months back reported in another paper what should be the statistics of the electron." And the gentleman that Dirac was immediately called it Fermi statistics. He didn't even dispute it. Okay? And of course now today we call it Fermi-Dirac statistics. Just like Bose-Einstein statistics for photons, for electrons and other particles which behave like electrons, we talk about Fermi-Dirac statistics. Satyendra Bose, I already mentioned his name, his work on the statistics of the photons, and so all particles which follow this type of statistics of indistinguishability. Okay? Because two photons are indistinguishable. So how do we count, the photon, how do we describe that state, etc. The statistics of that is what he developed, and that played a very important role in physics later. So all those particles are called bosons, which follow that statistics. Okay. Max Born, he gave the probability or statistical interpretation of this thing called the wave function. Okay. And this caused a lot of havoc later, because Schrödinger actually believed there are waves and wave packets, and even de Broglie believed in wave packets, but he said no, there is no wave or wave packet, this is all probability amplitude. So this interpretation of Born, while he did many other contributions, but this actually led to, you can say, modern day standard interpretation of the quantum mechanics. That this is psi is not a real wave function. Not only its complex value, but it is what he called as probability amplitude, not even probability. Okay, if you take a modular square of that, then you get the probability of finding that particle in a particular volume and so on. Okay, but this is now the standard interpretation of wave function, which has bothered a lot of people. That this whole thing later led Einstein to say, Einstein disputed it. He said, God doesn't throw dice, play dice. How can you, because there are many physicists, and even today, who believe in determinism, who believe that either it is this or that. How can it be both? Or how can it be sometimes this and sometimes that? So all this just means our knowledge of the system is incomplete. Okay? And so on. I'll come to that at the end. John von Neumann, who laid the mathematical foundations, he also laid the mathematical foundations of computer science, along with Turing and Church, but von Neumann's architecture of the computers is still the basic architecture of the computer. But he was a mathematician, he is known for his mathematical foundations of quantum mechanics. He cleaned it up and put it in rigorous mathematical terms in 1927-28. C.V. Raman, you know about the Raman effect, because it was very important that even studying the spectra of molecules, liquids and so on, that their vibrations and their rotations are also quantized. So when you shine light on them, that emerging light might have either lost some energy or gained some energy, and that is in discrete quantities. So it reinforces the quantum theory. So that is why many ideas, experimental work and even theoretical work take a long time to be recognized by peers and especially Nobel Committee. But he's got immediate attention. In 2028 or something he reported it, and 32 he got the Nobel Prize. This is very unusual. Okay? Most people I have listed got it 10 years, 15 years later. But Raman got, because it was a reinforcement of the quantum theory. Experimental verification of quantum theory. Compton, we did similar thing with the X-rays. X-rays bouncing off a crystal. Okay, that again some amount of discrete amount of energy fixed, which is related to the structure of that crystal, is absorbed, or added, and so on. So the X-ray coming out of reflection from this crystal will have a different frequency than what was shown on it, etc. Okay, inelastic scattering. What's called inelastic scattering? G.P. Thomson. He is J.J. Thomson's son, by the way, and so the father son, both of them got Nobel Prize. Now Thomson, he did experiment and showed actually that electrons also diffract like this. So what de Broglie had proposed, that you can have a wave associated with electron, was experimentally shown by Davison and Thomson in their experiment where electrons diffracted. Electrons showed a pattern which is just like any wave diffracting. Okay. C.D. Anderson, this is the person who actually discovered the positron, the physical particle, which was predicted by Dirac earlier. Chadwick first proposed that there is a neutral particle, not just electron and proton, there is a neutral particle inside the nucleus. Okay, so and called it neutron, and later experimentally also it was observed that the neutron. This is Yukawa, Hideki Yukawa with Einstein in Princeton. Yukawa first developed the theory of nuclear forces, a Japanese scientist, and for which he proposed a new particle called meson, a pi meson, which is exchange between protons and neutrons and so on, and that binds them together. Otherwise, why should two protons sit inside the nucleus? Why don't they kick each other out? After all, they are both positive charges. So there is some other force, stronger force than electromagnetic repulsion, which is holding that nucleus together, which is what is called the strong force or the nuclear force. And for that, he proposed the theory of exchange of mesons. So that was again a big breakthrough in what is called quantum field theory. That there is an exchange of particle is equivalent to an exchange of energy, which leads to binding of those two. Okay, relationship between those two. And later that pi meson was discovered in cosmic rays, and other mesons were also discovered. Okay, but that was theoretically it came out of Yukawa's theory. Feynman, of course, many of you have heard of him, great physicist, and he and two others, Tomonaga and Schwinger, developed the theory of interaction between matter and radiation, which is today called quantum electrodynamics. But I am showing only his face here because he is another great scientist who said that nobody understands quantum mechanics. You read his famous Feynman lectures on physics given at Caltech. They are absolutely wonderful books, on to study most of the classical and even quantum physics. Though he gave it at undergraduate level, but he says that nobody understands quantum mechanics. Okay, and a great practitioner of quantum mechanics itself, where they were able to unify that kind of beta decay type of interactions, which are called weak forces and weak interactions, and electromagnetic. Because electromagnetic theory behaves in a different way. Nuclear forces and weak forces, they behave in a different way. Gravity behaves in a different way. So a theoretical physicist's dream is to unify all of them. So unification of all of them has not been possible so far, but they were able to at least unify electromagnetic and the weak interaction. Okay. Now I am again showing Abdus Salam was a Pakistani And Steven Weinberg, again I'm emphasizing him because he is another great physicist of the 20th century who also said that nobody understands quantum mechanics. Okay? Now, okay. So why? What are the problems? So I'll just briefly, so we have talked about achievements all this time, very triumphal, it has led to so much change in quality of life. Is fundamentally, if you see De Broglie, Schrödinger, Einstein, Feynman, Weinberg, they all had problems with the interpretation of quantum mechanics for various reasons, different reasons. Okay? But fundamentally, one problem comes is because of the duality. Because classically you think the matter is independent of the object is independent of the subject, the observer. So the state of the matter should be unique. And you are trying to probe it through your experiments, etc. and discover what is the state of the matter. This is the realistic or materialistic view of the world. And that has been the traditional view of science. Traditional view of scientific inquiry. Okay? But if you say that I am not able to say what the state is, then maybe your knowledge is incomplete. So Einstein published a paper saying that quantum mechanical description of reality is incomplete. Because we are not able to do number of things. There is also, he raised the issue of locality and various other things also. But basically that if you are not able to say what it is it a wave, is it a particle? Because these are diametrically opposite concepts. Particle is here. It has a mass, it is a location, and wave is everywhere. How can it be everywhere and also here? How it being everywhere is also true, and it being here or somewhere here, even if you follow imprecision like Heisenberg, and say not exactly here but somewhere here. Okay, in this he gave an error, this thing. Okay, in this we can locate it, but not precisely, he said. But how can it be here and also everywhere? So this duality is what is totally unacceptable to the classical mind, and classical mind still guides scientific inquiry. Classical epistemology, classical philosophy still guides determinism, still guides philosophy, scientific inquiry. So, if we say we don't know for sure, sometimes in some experiments it behaves like waves, in some experiments it behaves like particle, whether it's light or the electron, then you can say our knowledge of that thing which we are calling electron or we are calling light is incomplete. Okay? Now, here comes Niels Bohr and he gave this principle of complementarity, where he says that is the way nature is. Now, this is not an explanation. He is just describing the ignorance by what I would call the ignorance of the state by saying that's the way it is. You can, it can be both. You can have both qualities, one quality and its exact opposite coexisting. And you need both to know that thing. This is his thing. In fact, this reminded me of Jain philosophy. In Jain Darshana of Anekantavad and Shyadvad, they talk about opposite qualities being existing in the same object. So, probably if you are a follower of Jain Darshana, which is called Anekantavad and Shyadvad, you will be okay with this. Okay? Because Jain Darshan talks about it. Exactly this. It leads to multivariate logic. But if you are trained in Aristotelian logic, of binary logic, of true or false, black and white, then you can't say black and white can coexist. You can talk about in some places things being grey. But the greyness can be measured also, no? The amount of how much of black and how much of white is mixed to produce a particular shade of grey can be measured also, no? So these are some of the troublesome questions which have led to many founders also. In fact, Feynman said most physicists use quantum mechanics. Why? Because it gives the right results. You calculate, you can verify it to the 8th decimal place, 10th decimal place, you are correct. So pragmatically you accept its philosophy also, because it works. Right? That is pragmatism. Something is right or true because it works. Whether, it is acceptable in other philosophical ways or not, moral ways or philosophical ways or not, because it works, it's right. Right? So he says that most cases are pragmatic in his lectures on physics. And this other thing also comes, the role of the observer. Now we always say that the observer and the observed, the subject and the object, there is a distance, object exists independent of subject. Right? This chair exists whether I look at it or don't look at it. I can't say when I look at it, chair comes into being or chair disappears. The chair exists independent of my looking at it, my observing it. Right? So, whereas if you follow the logic of the traditional Bohr, Heisenberg interpretation of quantum mechanics, then it looks like it depends on the observer, what he is looking for. Now, if you are going to see what you are looking for, then what is reality? Because you have determined what you want to look for. Right? It's not that reality is not independent of you, independent of your consciousness. Matter doesn't exist independent of your consciousness. So, this totally the role of the observer in measurement. Normally in classical physics, what do you do? When you take a temperature of a person, right? The thermometer bulb absorbs some heat from your body, but that is so small that it's negligible. So say, body's temperature is 98.6. Though you know a little bit of that heat has been taken by the bulb of the thermometer. So it's not exactly 98.6, it may be like some 8 decimal place, 10 decimal place, up or down. Right? But here it is a totally different way. The observer is seeing what he wants to see. I mean, if he is looking for a wave and designs an experiment, he will see wave-like properties. If he is looking for a particle-like properties and designs an experiment, he sees particle-like properties, which in your mind at least they are opposite. How can the same object have opposite qualities? So these are some of the, you can say, troublesome questions. And some of these, I am not going into it. This is called the double slit experiment. Feynman used it a lot. This you can say the thought experiment. Used it a lot to illustrate these dilemmas, philosophical dilemmas. Okay, that if anyway, so I'm short of this is what normally happens, that when a wave hits two small slits, okay, fresh waves are created here. When these waves meet, they do not produce. Normally, if you are shooting electrons or particles from here, some particles will go like this and produce a bunch here. Some particles will go through here and produce a bunch here. So you'll get two distinct spots on your screen. Here no, here you are seeing bands. Some are bright bands, some are black bands. So this means some places they are cancelling each other. Is an electron destroying another electron, and in some places not only adding but it's actually doubling it is getting, you can say, amplified in the bright spot. So these are commonly explained in wave theory. But if you thought that what you are shooting is bullets are not waves, right? But the Feynman proposes that if you sit here and observe from where this electron came or where this photon came, it came through this, how many photons came through this and how many came here, and so on. Then he says you will get a bullet-like picture. Means if you look for the particle, the wave interference pattern disappears. Then it suddenly starts behaving like the particle. But if you don't look from which hole that particular photon has gone, then it produces an interference pattern. That means you designed an experiment where you are not interested from which hole the photon or the electron traveled. So this kind of observer and observation and the way you are observing affecting the end result is unprecedented in physics, and also is very disturbing to human mind which wants cause-effect relationships, which wants something leading to, some definite answer. You can say, I don't know the answer. You can't say the answer is a mixture of both. And that's how, to mock this, Schrodinger created that famous thing, and which recently cartoonists talked about Strait of Hormuz as the Strait of Schrodinger. Because you don't know whether Hormuz is closed or open. Trump says it's open one day and the next day he says it's closed, right? A few hours later. Then again he says it's open. So somebody made a cartoonist in India, showed it as a Strait of Schrodinger. He created a cat experiment where it was not sure the cat is dead or alive. So he said, according to quantum mechanics, cat is both dead and alive simultaneously. Okay, till you look into it. When you look into it, it may be dead or it may be alive. But till you don't look into it, inside the box, it may be both dead or alive. The superposition of both dead and alive is actual state and so on. So these are some of the troublesome things. But when we use this for calculations, they give very verifiable results. Okay? So this is what is also very intriguing. If they did give verifiable results, we would have called it metaphysics. Right? Physics is verifiable, metaphysics is not verifiable. You can postulate whatever you want. Soul is here, it goes there, it travels here. You can say anything you want, right? So you can say, in fact, somebody talked about consciousness of the electron also. Electron consciously chooses to go through this. Okay, because if you stretch it, it can lead to all kinds of idealism and subjectivism. Anyway, so this is the famous paper Einstein wrote with Podolsky and Rosen called UCR. Questioning the completeness, and that's it. Thank you.
Thank you so much, Professor Kanavi. That was quite a scintillating talk, which took us very comprehensively through the whole history and the relevance and so on. And I think it's very important in terms of science communication, more and more that we keep, we discuss these things and draw people in. I think it's really the need of the hour. So thank you so much. That was wonderful. But we have very eminent scientists and physicists right here also, apart from our own NIAS staff, also visiting from Indian Institute of Science, Professor Krishnamurti, Professor Anand, and his colleagues here from France. So we could also draw them into the discussion. So over to you, please.
If any of these well-known physicists are going to get up and say something, I will ask them to explain it themselves. Don't ask me questions, okay? Because they are much more accomplished practitioners of quantum mechanics. All their life they have spent in that. So I have given a journalist view of quantum mechanics.
The question of the philosophical aspect that you mentioned about the Jaina tradition and those debates, evidently they were not thinking about the material world and carrying out experiments and so on. So in what context? Whereas if you say Aristotelian logic, Aristotle had the idea of doing some experiment, whether it is dropping bombs or whatever. So could you just tell us a little bit more about the schools of philosophy and what they were? And how do you think it could get applied, in the resolution of such philosophical difficulties?
See, so far, of course, we all know that there are many questions for which there is no yes, no, true, false answers. Many questions in life. Okay. So, but what is reality? Is it this or that? Fuzzy again meant that there should be some weighted averages, there should not be 0 or 1 probability, there should be something in between and all that. Okay? Now, I don't know more than this to explain to you, I'm not an expert in this. But the people, he was laughed out of Berkeley, literally, almost. The chairman of the Department of Electrical Engineering in Berkeley said, what Zadeh is talking is, he has smoked something. He said it is a cocaine of science, he said. Okay? But So I printed it and then Japanese picked it up and Japanese used it in all their gadgets. So every like Japanese washing machine, microwave, television set had fuzzy logic and chips based on fuzzy logic, etc. So where it led to adaptive, it gave the ability to do adaptive controls. Okay, it's not just 0, 1, but there can be weighted means between the two. But when Zade was asked what inspired you, he did say Jain, but he said some Eastern logic systems. But we know that Buddhism also talked about 4-valued logic, which is called Chatushkoti. And Jainism talked about 7-valued logic, it's called Saptabhangi. And it also gave a philosophy of Anekantavad long ago, I mean, several centuries or a couple of millennia ago, because Jainism is a very old tradition. That where they talked about a thing having a particular quality and also its opposite. But it says our ability can see only one quality. Okay. But then it led to another philosophy called Anekantavad, again in Jainism, which said that since our understanding is partial, our grasping of the truth is partial, then there is no monopoly, there is no absolute truth. Okay? So if you are looking at a phenomenon and you say it is this, then another person looking at it from a different angle, different perspective will say no, it is that. Now they say both are correct. From their vantage point, he is seeing this and you are seeing that. But if you actually integrate the 360-degree view, then you might get closer to reality. And the parable that is given to explain this is the blind man and the elephant. Okay? In Indian philosophy, this is an often used parable where the blind men are told to touch the elephant and describe it. So one blind man touches its tail and he says, oh, it's like a broom. Another one touches its feet and so oh, it's like a pillar. And somebody else touches its trunk and says it's like a snake, a python. Somebody else touches its ear and the ears are big, so he calls it, it's like a huge plate and so on. And each one is true. None of them are telling a lie. But each one is having a different approach, a different perception of that. Now, another thing, you develop it further. If you add all that perception, you still do not get an elephant. Okay? So, absolute truth is unachievable. You can only, in asymptotically reach the absolute truth. Okay? The reality, the absolute truth, you asymptotically can reach it, you can only have partial truth. Now, you can say, hey, this doesn't guide me in life. After all, I want to decide. Should I take this side or that side? Okay, in a polarized world, any action requires a decision. So this is a theory of inaction, paralysis. So all points of view are equally valid. Okay, so this is one way of critique of that Jain view. But the Jain view has its own merits. It says that because no one has monopoly of absolute truth, everybody has partial understanding of that truth, that means it's democratic. That means you respect the other person's view also. Don't say that I am correct and you are wrong. That won't be accepted. You can say, you can even impose it with force, absolutism. But no, if you accept that my truth is relative, other person's truth is also relative, then at least you examine his position objectively rather than dismissing it. So it's more democratic for a democratic, peaceful coexistence in a society without conflict. Then this giant Anekantavad gives away. But still, finally when we have to act, then you might have to take the democratic recourse of majority and minority. Okay? At least temporarily you can say majority seems to feel this way and minority this, so let's go ahead with this, while we are also recognizing minority point of view, etc. So there are merits in both the critique of this Anekantavad and in Anekantavad itself. But this was applied on the theory of reality and consciousness. how consciousness is trying to understand reality. That time it was not an experimental thing. It was logically argued. Just like for example, we talk about Indian theory of atoms or Democritus' Greek theory of atoms. Indian Kanvi Rishi talked about atoms. But Kanvi Rishi did not do experiments with atoms. Okay? Like the chemist Faraday or Dalton or anybody else. He argued logically. The process of cutting matter has to stop somewhere. Why? Because this is a grain of sand. This is Himalaya. If this can be divided infinitely and if that can be divided infinitely, then there is no issue of size. This is also infinity, that is also infinity. And uncountable infinity. Okay? So, how do you compare to uncountable infinities? This is pre 1800 years before George Cantor, okay, and Aleph Knot and all these other systems. So, in the real world, because there are sizes, there is finite objects. So then finite objects can be compared. Then the cutting has to end somewhere. So you can say, yes, Anu, Paramanu is where cutting stops. Which is also a Greek concept. Atom, no more cutting. Okay? Democritus' concept was also that. Kanada's concept in the Vaisheshika Sutra is also that. Okay, it has to stop somewhere. And that is what he called Anu or Paramanu. And then you can say in the grain of sand it is 1 trillion, in Himalaya it is trillion or something. So you can compare two finite things. Otherwise you cannot, there is no comparison. All are infinities. Okay? So logically he arrived at that. So similarly many things in these ancient philosophies are not done through experimentation and observation and verification. Many things are done for logical reasons and consistency reasons and all.
So I want to make two comments. One is about the observer. I mean, it's really a problem with interaction between the measuring apparatus, and I know it's normally posed as observer, but I mean, we should remove the human element from it. It's really a question of when all of the language used in science and continuing into quantum mechanics, the measurement language is a language of classical mechanics, because it's something that because of the human element that was involved in the measurement. So it's really what is seen as a state of a classical system. So the problem comes because of classical system, which is big, interacting with quantum system, which is tiny. So this whole thing of measurement not affecting the object being measured is actually connected with that. It's not because intrinsically when we say we measure something, we actually have in mind that it's a classical apparatus interacting with the thing. So if you take that interaction into account in detail, I don't think there's any paradox or fallacy, etc. in that thing. And in some of the stuff that Feynman is talking about, it is like that. I mean, when we talk about double slit experiments, why the interference pattern disappears is because the act of observing, I mean, not the human thing, but the interactions that are involved in observing whether it goes through one slit or another, actually messes up the state of the quantum state of the thing. So otherwise, at least my understanding is that there is a quantum reality, a quantum version of reality which we are not used to, so we are uncomfortable with it. Which is that there is a particular state that describes the quantum object in question, and starting from that state we can predict consequences of all measurement, which means interaction of all classical things that we are familiar with that quantum object. And that is the quantum reality of that state. So, there need not be any, paradox or big debate around it. And I think some of this thing will get clarified a lot more because of the advent of quantum computers and a much more clearer understanding of even the Einstein EPR experiment, etc. I think it will emerge slowly so that people become comfortable with the nature of this quantum reality. But at least to me, that's the way I look at it. Yeah.
Yeah, one just note I want to add detail. This is more or less what Bohr said, complementary. Reality is that way, I think, complementary principle. And on the opposite side, following Einstein's thing that it is incomplete, the people who started saying there is an underlying reality which we are not able to see, and posited hidden variables and all that, David Bohm and all that work, but that also could not go too far further.
Yeah, but then some of that, so whenever anybody had, so the question is, whenever anybody came up with an underlying thing which has measurable consequences, that has been disproved.
Yeah.
So if you make an underlying picture of reality which has no measurable consequences, then that's philosophy, it's not science. So you can debate endlessly about it. I mean, have fun even doing it. I'm not saying one shouldn't do it, but it's in the realm of fiction, just entertainment, whatever, philosophical entertainment. It's not science.
Yeah, that's true. At the same time, the reason I showed Feynman and Weinberg is that this issue didn't get settled in 30s when Einstein raised these issues, completeness and all that, because Feynman also raised it, Weinberg also a decade or two later raised this, that don't understand. What he meant, don't understand, is these types of issues.
Yeah.
Not particularly calculable things, but which bother determinism and realism, idea of.
One can raise philosophical issues about what does understanding mean.
Yeah, sure.
If AI can do everything that we can, I mean, does the AI understand? This is another facet of many of these questions, ontological questions, which are going to come up in the context of AI, because it's a bunch of neural networks, the same way what we call our understanding is an emergent quality coming out of our neural networks. So we don't know what's happening inside our neural network either anymore. But I'm saying the same thing is true of what happens in the thing. Somebody very young performing feats of incomparable, because that person's neural network is doing whatever. We have no clue. Without further investigation, measurements, etc., we will somewhere we might quote unquote understand, but I don't know whether it is. It will be very complex reality.
See, there is one issue about which you yourself have worked in phase transitions, singularities, critical points and so on, as I understand. That so far at least, physics works till the end of this phase and then the beginning of that phase to the next.
So the fundamental theory still works. The noise theory by Shannon application, everything works. So looks like the classical mechanics, classical systems are working beautifully. In what way do you think? I'm not looking for an answer. If you have, we can discuss whether there will be a great improvement because of the quantum. Thank you.
See, when you are dealing with this issue, remark which Krish made about classical large objects, we do not need quantum mechanics to describe them. Even today, if you are doing Mangalyaan calculations, you do not use quantum mechanics, right? Use Newtonian calculations for orbits and positions. There may be perturbations due to other things, but you're still using classical mechanics. And you're still using classical electromagnetic theory for the signal and all that. So, only where those approaches break down, then you start looking for answers, and actually the macroscopic, atomic and subatomic level phenomena, this thing broke down. Classical explanations broke down. That's why the new theories had to be developed, and the new theories explained it. So even though they raised some troublesome questions, it got accepted. Today, just because these questions are there, nobody will say, I will not solve the Schrodinger equation or learn the Schrodinger equation or any other thing in the quantum mechanics. Okay? Feynman practiced it. Weinberg practiced it. They got Nobel Prizes for practicing it. Okay? But they had these philosophical questions about it, about completeness and reality and what is the role of the consciousness regarding matter, etc. Now, as far as the very semiconductor business, which depends on barrier penetration, okay, that cannot be explained classically at all. The electron cannot go up the hill and come down. The tunneling is a pure quantum effect. Okay, so that is why we talk about transistors and semiconductors being a quantum effect, whereas the old electronics, valve electronics had no quantum mechanics. At least did not need quantum mechanics to explain the behavior of triodes and diodes and pentodes and all that, the old things. But these produced much more capability and used less power. The first computer, Princeton computer, which was used by under supervision of von Neumann, and they were using it for Manhattan Project calculations. It was huge, and they were putting these these pedestal fans, which are used in shadis now, shamiana, to blow away the heat, because the valves produce so much heat, and a lot of the valves used to get burned. And once actually a moth went into this wind of the fan. One moth got swept into it and went into electromechanical relay. Even the relays were electromechanical. So it shorted and the computer crashed. And when they found the moth, they called it a bug. And today also computer scientists use the word bug when a system crashes, because actually a bug had crashed the original Princeton computer. Okay. So, but when you found semiconductor transistor circuits and later, the chips came in, IC circuits came in, and so on. Now, of course, you have billions of transistors on a single chip. Your mobile phone has more power than computing power than what was used in many of the NASA projects, etc., or even older supercomputers, etc. But that's all due to the development of the miniaturization, but the underlying physics is quantum. That's all. And communication, lasers, and all these things which totally changed communication. Otherwise, copper cables were working. So copper cables could not do what the fiber optics did.
So, well, I
have a question.
please.
Oh, I don't.
No, please.
I just want to add one thing about what you talked about earlier, like saying the Feynman interpretation solves the observer problem, and I think it solves also the problem with particle and wave duality, because when you think as Feynman, you think with field and with quantum electrodynamics or quantum field theory, and so there is no more this logical problem of the duality of wave and particle, because everything is just field and excitation of fields. So it solves the problem of the observer with interaction, but it solves also the problem of the duality of particles and waves. But I don't know if it solves the problems you talk about with light and matter. But those two problems, I think, are solved with this interpretation of quantum mechanics, which is a lot after Einstein or thing you talk about.
Yeah, quantum field theory tried to combine the two. I mean, the field theory originally was meant for continuous fields, right? The old fluid dynamics and all the aerodynamics, everything was for continuous fields. But when you quantize the fields, then you talk about exchange of particles, attraction, repulsion as exchange of particles, etc. So it's a quantum language being used to explain even attraction, which was at one time considered action at a distance, right? That became, no, it's an electromagnetic interaction. So it is a finite speed of light is what is carrying it, etc. So, I mean, in my mind it's not solved, okay? Duality is not solved in my mind. Maybe it is solved in many other people's minds. So,
At a macro level, Shannon's sampling theorem integrates quantized and the wave. In fact, it's a good example at a macro level. So probably we can extend it down, because it does explain how a discrete digitized data can be represented as a wave.
yeah, this problem of the, again, discrete and the continuous. The duality of the discrete and the continuous is another big philosophical problem. Okay, because in physics at least, what we thought continuous turns out to be discrete at certain level, and what we thought discrete also like has continuous properties of the continuum. So this gets, if the categories become absolute, then why even this implication or overlap is there is for old minds like mine, it's troubling.
Thank you. Well, as I said, I've been working mainly in archaeological material science, so quite removed from all this. But I was just wondering about this buzz about quantum entanglement, which won the Nobel Prize also in 2022. And because Einstein was quite disturbed because he was, concerned about this thing of particles moving faster than the speed of light. But now we hear about it being used in quantum computing. What about the future? They talk about quantum internet and also quantum entanglement in terms of space and things. So I don't know. Just wanted any.
See, we'll
Also from you and the audience.
See, I am a reporter. I am not a theoretician. So I report what exists, a journalistic mind. So when actually, see, the research into quantum computing came because of Peter Shor's work and all that, saying that the factorization problem, which will take almost infinite amount of time for the existing computers, can be done in finite time by quantum computers, etc. And then Grover algorithm and Grover's theorem, that totally unstructured data down. From that you can extract useful information again in finite time if you use quantum principles. So this has generated a huge amount of money going into quantum computing research. Okay, so something which was esoteric, it was actually proposed in 1980 or 82 by Feynman himself. Feynman in one of his lectures talked about quantum computing. We may be able to solve this. But it became much later in the late 90s. Computer scientists took to it, and then even physicists said that they are talking about computer science, quantum effect. Maybe we can also add our knowledge of quantum phenomena to what these people, computer scientists, are talking about. But the funding came because if you can break the factor, the encryption which is done using this factor theorem, that then entire intelligence and military communication, which is now encrypted, can be broken very easily with quantum computers. So also all the financial data. So the encrypted financial data, which is used now in banking and stock markets and all that cannot be broken with quantum computers. Whereas with existing computers, it will take zillions of years. Okay, you can keep increasing the number of the encryption length that you are using, 256 bits or 1024 bits, and keep increasing that complexity right now. But if you start using quantum computers, then the theory says that it can be broken in finite time. And if you got big enough quantum computer, not only finite time, but you might do it in usable time. Means in a few seconds you can break the Wall Street communications and all the banking transactions and all the military communication, then that power will rule the world. So that's why a lot of money is being pumped in by all the major powers into this kind of thing. But when a real working now, of course there are so many people who are claiming that we have built 5 qubits, 120 qubits and this, that. But there is still no commercially operating quantum computer as far as I know, which is breaking these things. They are still proof of concept type of things. So, is there a hype being created because funding is coming? Okay. A lot of work in the 60s and 70s in America itself was funded because the guys who were going for funding to DARPA or whatever used to say, oh, Russians are ahead of us. In fact, the person who funded a lot of AI projects in DARPA told me that, I was in charge of funding that, and it was because people used to come and say Russians are ahead of us. So can we first natural language processing and translation work was to first understand what the Russians are writing in their communications and even research papers. Can we translate Russian into English, American English, almost, in finite time and all that. That's how natural language processing started and got funding from Defense Department and all that. So, is it that kind of thing that's happening now, hype being created because, oh, Chinese are ahead of us and no, Americans are ahead of us, that thing? Or is there really underlying solid science, both in theory and in this thing work? Time will tell. Okay. And when I see it, I'll say we have got it. But till that time, my fingers are crossed. Maybe it's premature. There may be premature hype because, for example, 25 years ago, there's a premature hype of internet, about internet. Internet will do this, that, and everything will become like this. And then the market crashed. Then everybody forgot about it. But actually work was going on. So today we are seeing so many things getting applied 20 years later, which has made life different because of internet itself. Forget AI. Right? So, but now you don't have to convince anybody that internet is useful or bandwidth is useful, so all these submarine cables are useful, all DWDM, all that dense wave, wave vision multiplexing is important. All that sort of thing which was talked about 25, 26 years ago, now is become routine. But that time there was a hype and super valuations in the Wall Street, and then there was a crash. Now today there is something similar going on in AI and all that. So maybe there is, looking at these cycles, one can say that maybe 25 years, 30 years later we'll have tangible effects coming out of this. It is like talking about fusion research. Now fusion research, will fusion be powering us? Maybe. 50 years later, 100 years later. Physics of it is, we know, but engineering of it has not been possible so far.